All right, so we'll talk a little bit about friction in this PowerPoint. It's part of our equilibrium first law unit, but I think it's important to share some information specific to friction that'll allow you to do well when we start getting into the harder math of the free body diagrams and things like that. So we should already know there are two types of friction. We know that there's static friction, and we know that there is kinetic friction. Static friction, we know if we push an object, if we have an object on the ground, and that has a certain weight, we know that if we push it with an applied force, let's say to the right, we know that as we push to the right, that the friction force, in this case it would be static because we're saying it's not moving, we know that the friction force would increase. The more we push, the more it's going to resist our motion until we reach what's called static friction max. And static friction max is the point at which if you go past that, the object will start moving. In other words, it will accelerate. So for the acceleration to occur, the applied force has to be greater than the static friction force max. Kinetic friction, it is the value that's always less than static friction. We know that for an object to accelerate, that the applied force has to be greater than the kinetic friction. Think about if you were pushing on a car and you let go, you stop pushing on it. Well, the car's going to roll, slow down, and eventually it's going to stop. It's going to come to a stop. So the kinetic friction will slow the car down, causing it to come to a stop. But as long as you keep on applying the force and it's greater than the kinetic friction, the car is going to accelerate. If you want to push it at constant velocity, straight line, no speeding up, no slowing down, then you would have to make the applied force the same as the friction kinetic force. Let's also remember that the reason that the kinetic friction force is less than the static friction force is once you get an object moving, the first law takes over, the law of inertia, where it wants to keep on moving once you start moving it. So it's much easier to keep it moving than to start it moving. It's much easier to push a car that, say, run out of gas while it's moving than get it started. So what factors affect friction? What factors affect friction? Well, there are two main things. There's the normal force, and we know that the normal force is the force of an object surface. So if this crate is sitting on a surface, we know that the normal force would push perpendicular to that surface. Of course, the weight force would push down or pull down. But remember, the normal force is the force of the surface pushing on the object, perpendicular to the object, or perpendicular to the surface. And then whatever the surface is made of. So the surface composition, and that should be common sense to you. You would know that ice has less friction on it than gravel, like an asphalt road. You know that it's much easier to drive on an asphalt road than it would be an icy road because the friction is much greater on the asphalt road. So normal force and surface composition are the two main factors that affect friction force. And believe it or not, we can change the normal force depending on the situation. If we take a look at our crate here, the one on the left, we have a crate that is 50 newtons. So we know that the 50 Newton force pushing down on the table is 50 newtons. The normal force has to be equal to 50 newtons because we know that this object is in equilibrium. It's not moving. So whatever the weight force is, in this case 50 newtons, the normal force has to equal that. Well, what if I come along and I push down with my hand? What if I push down with, say, 200 newtons of force? Well, now we have the force of the crate itself, the weight force, and then we have my applied force. Well, what do those two add up to? Well, they add up to 250. And as long as the crate isn't moving, as long as we're not causing it to move or accelerate, then the normal force is going to change. The harder I push down, let's say I push down with 300, the more the normal force is going to be. If I push down, say, with less force than 100, 250, let's say I push down with 100, then I will be 150 normal force. Again, it would be the 100 from me plus the 50 pulling down or pushing down, and then the table would be pushing up on the crate with that same amount. So the normal force can change. You can also change the normal force if you are pulling up. Let's say there was a rope attached to the crate and you were pulling it this way and it was constant velocity. Well, since you're pulling a little bit with a y component up, right? This will be our y component, this will be our x component. Since you're pulling up a little bit, you are causing the weight, the apparent weight, to change because you're pulling up a little bit while you're pulling to the right. So you would actually cause the normal force to lessen than the weight of the object because you have a little bit of y component pulling up on that object. So stop and think about this question, and then we can answer it. Which vehicle will have more traction in the snow? A vehicle with front-wheel drive or a vehicle with rear-wheel drive? Now remember, front-wheel drive is when you have the accelerator and you press on the accelerator and the front wheels spin. Rear-wheel drive would be if you press on the accelerator and the rear wheels spin. So a front-wheel drive, the front wheels drive the car, make it go. On a rear-wheel drive, the back wheels make it go. So pause the video and see what you think. So you got to think about how the weight's distributed in your car. In the car here, the engine is located in the front. And the rest of the car, although it does have quite a bit of mass, the mass is more concentrated on the front. So if the mass is more concentrated on the front, we're going to have more weight distribution towards the front. Well, what's that going to do to our traction if we are pushing down on the front more than the back? Well, it's going to make our traction greater because we're increasing the normal force by pushing down more. So hopefully you answered that the front wheel drive is going to have more traction because the engine is over the wheels and they're pushing down on the wheels, causing it to hold on to the snow better. Friction force is also related to the smoothness of the surfaces, and we have something called the coefficient of friction. And the coefficient of friction is abbreviated with a little mu symbol, and that mu symbol can be static or kinetic. So you have the coefficient of static friction and you have the coefficient of kinetic friction. It's a scalar quantity, doesn't have a unit, it's just a ratio. And it's the ratio of the friction force to the normal force between two surfaces. So whatever the friction force is and whatever the normal force is, it's just that ratio between them. The coefficient of static friction would obviously be for an object that's not moving, and the coefficient of kinetic friction would be for an object that is moving. The lower the value for the coefficient of friction, the slippier the surface is. So ice, your rubber soles of your shoes walking on ice are going to have a much lower coefficient of friction than your rubber shoes walking on, say, concrete, because the concrete surface has more friction, and that's going to cause the coefficient to be higher. So the higher the value, the coefficient of friction, the more stickier the surface is. So here's some examples of some various coefficients of friction. Steel on steel, we see it's 0.74 for static, and we see it's 0.57 for kinetic. And we would expect the static to be more than the kinetic, because we've talked about how kinetic friction values max are smaller than static friction values. Much easier to keep something moving than to get it moving. And you can see that our values can change quite a bit. If we have Teflon on Teflon, Teflon sometimes a coating you see on frying pans. It's used in plumbing with Teflon tape. But we noticed that the Teflon on Teflon, we don't see a difference in the numbers. Kind of an interesting thing there, but we do see it's very, very low. We see it's very low. And then our synovial joints in our elbows, our knees, our shoulders, our hips, the things that allow us to move our joints are very low. And we would expect them to be very low. You would hope that the joints in your hip would be very easy when they're rubbing against each other. The friction would be very low. If the friction is higher, if your synovial joint coefficient of friction values get higher, that means you're going to have trouble, like arthritis. So you might need a hip replacement or something like that, or shoulder, same sort of idea. So we would expect this synovial joint to be, the value to be almost nothing. And that's good because that means we can move our joints without any problem. And of course it changes depending on the type of material. Copper and steel versus steel. On steel you see there is a different value. Here are our formulas for coefficient of friction. The static friction force is equal to the coefficient of static friction times the normal force. The friction kinetic force is equal to the coefficient of kinetic friction times the normal force. We could, of course, rearrange this if we were solving for the coefficient, and we would see that the friction force is exactly, or the coefficient is exactly what we said. It's that ratio between the friction force to the normal force. And the same thing you would see down here. So to recap, we know friction acts parallel to the surface and always opposite the motion or intended motion when we're drawing our free body diagrams. We know that the friction force is directly proportional to the normal force, meaning the more normal force you have, the more friction force you're going to have. We know that friction is related to the surface composition. We call that the coefficient of friction. We use a mu symbol to help us identify it. The higher the mu value, the larger the friction force. The lower the mu value, the smaller the friction force. So let's go through a few sample problems and see if we can clarify all of this stuff. A 250 Newton crate sits on a factory floor. It takes 170 newtons to set the crate in motion. Calculate the coefficient of static friction between the crate and the floor. All right, so what are we given here? Well, it always helps to draw out your free body diagram when you are doing a problem like this. So I'm going to go ahead and draw it out. I have a crate sitting on the surface of a factory floor. And I'm going to draw my weight vector, remember, straight down. We always draw it straight down. And that equals 250.5 newtons. And we're applying a force to it to make it move. And we know that the applied force is going to be lateral to the surface, so we're going to call that applied force, and we're going to say that's 170 newtons. Now you might be asking, why am I pointing it to the right? Well, I'm just preference. You could point it to the left if you wanted, it really doesn't matter. Is there a friction force here? Well, if the box is moving along a surface, we know that there has to be a friction force, and which way is that friction force going to go? It's going to go to the left. It's going to be opposite the motion of the object. So the friction force Do we know the friction force? Well, we don't know the friction force yet. We're going to find it. And then, of course, we have normal force, which is pointing up. And we're going to label that Fn. And that's everything that we know. So what we're going to do, and this is something you're going to have to learn how to do for first-year physics students, very common, is we're going to have to sum the forces. We're going to have to do some math to help us figure out various vectors and components acting on the box. Now, it doesn't matter where you start. I'm going to start on the y-axis. And the y-axis is where the normal force and the weight force are. So we're going to sum the forces along the y-axis. So we're going to take our weight vector and we're going to subtract it from our normal force vector. And the reason, we're saying sum the forces, and you see I'm subtracting them. It's not really summing, but really it is, because the vectors are pointing opposite ways. So obviously that one's going to be negative, one's going to be positive. That's the idea. And what would the sum of those be if this is an equilibrium? Well, it would be 0. Well, do I already know the weight force? I do. It's 250.5 newtons. So what is my normal force? My normal force is 250.5 newtons. So we already know the normal force. Now remember, we're after the coefficient of static friction. And we know that to get the coefficient of static friction, we need two things. We need, from our formula, we need the friction force, and we need the normal force. Well, I've just took care of the normal force, so I know that's going to go down here, 250.5 newtons. And what else do I need? I also need the friction force. Well, on the horizontal axis, the x-axis, we can sum those forces as well. We know that the sum of the forces along the x-axis is two things. We have our friction force minus our applied force are going to add up to 0. And I know that they're going to add up to 0 because just as it starts moving, we reach static friction max. So if that's the case, then if I know the applied force is 170, then I know the friction force is 170. And you could argue that it would be slightly less than 170 because it says that it starts to move when you hit 170. So just under 170 would technically be the static friction max, but that's something that we're not going to worry about. So I'm going to plug in 170 newtons for my static friction force. And we end up with a mu value of 0.68. And that would be the answer. Now remember, static friction force, the coefficient of static friction doesn't have a unit. It's just a ratio number. So that's going to be our answer for the first part. Once in motion, it takes 155.5 newtons to keep the crate moving at constant velocity. So let's draw another quick free body diagram. We know that, again, our weight is 250.5. That hasn't changed. We know that our normal force is the same value. That hasn't changed. We are pushing it to the right with an applied force. And the friction force is the other direction. And since it's moving, we call it a kinetic friction force. So let's sum our forces along the x-axis. Now, because it's moving at constant velocity, I know that it is at equilibrium. And that's important when we're summing the forces. So our applied force minus our friction force is going to equal 0. And I know that the applied force is 155.5. So I now know the friction force is 155.5. I also could sum the forces along the y. And prove that the normal force is still 250. So it's going to be weight force minus normal force equals 0. The weight's 250.5 newtons. And that means the normal force is 250.5 newtons. And I already wrote that over here earlier. But if this was a separate problem, you would still want to show you were summing your forces each time. And that's enough for us to find our coefficient of friction. So the coefficient of friction, of kinetic friction, is equal to the friction force over the normal force. And the friction force is 155.5. The normal force is 250.5. So when we divide those out, we get a mu k of 0.6208. And again, that would be no unit because it is a ratio. One of the things we noticed is up here we got 0.68, down here we got 0.62. And that makes sense because we said earlier that it is easier to keep something moving than it is to start it moving. So we would expect the mu k to be lower value, the coefficient of kinetic friction to be a lower value than the coefficient of static friction. All right, you're off to college and you need to move a large box filled with your books. The box weighs 25 newtons and is sitting in your room, has a coefficient of static friction of 0.55. How much force will you need to apply to set the box in motion? All right, so let's go ahead and draw our free body diagram. Get used to this. We always need to do this. We're always moving boxes, lifting them, sliding them in physics, just the way it is. And I have my weight vector. And I know the weight is 25 newtons. And obviously I have a normal force vector pointing opposite that. How much force will you need to apply to set the box in motion? So we're saying that it's static at first. And we're going to move the box to the right. So I'm going to apply a force to the right. And which way will friction go? Well, friction is going to be going opposite the intended motion. The intended motion is to the right, so friction force is to the left. And they give us the coefficient of static friction is 0.55. All right, so I'm trying to find FA. I'm trying to find how much force I'm going to need to apply to set the box in motion. Well, I got to sum my forces. So let's sum along the y first. The sum of the forces along the y. Well, FW is along the y, and if I subtracted the normal force from that, I'm going to end up with 0 because this box is in equilibrium. FW was already given. It was 25.0 newtons. Normal force is going to be 25. Simple math tells us that we can subtract the 25 to the other side and figure out that the normal force is 25. Sum the forces along the x-axis. Let's see, we have FA and we have friction static, pointing the opposite direction. We know that they will equal 0. So what are we going to plug in for FA? What are we going to plug in for FRS? We don't know either one. We don't know either one. Is there a way that we could find one of the two, and that would allow us to find the one left over? Well, let's think about this. We know that the friction force is equal to the static coefficient of friction times the normal force. Well, if I wanted to find the friction force, I would need to know the static friction coefficient of static friction, and I would need to know the normal force. Do I know the normal force? Well, the normal force is right there. Do I know the coefficient of static friction? It's right there. So I can plug and chug, and I can figure out the static friction force. So it's going to be 0.55 times 25 newtons. And the static friction force is equal to 13.75 newtons. So if I go back up here to my summing forces, I now know that the static friction force is 13.75 newtons, which means if I'm trying to keep it moving, or if I have to apply a certain force to get it to start moving, then I know that the applied force is 13.75 newtons. So really, what we're saying here is that the applied force is 13.75. Once you reach that, it will start moving. So just under that, it's still not moving. So when we say how much force will we need to apply, we need to apply that much. And that's the applied force. Just past that is where we're going to get the box moving. Slide, we solved for applied force and we got 13.75, which is, so this involves our same box from earlier, from the previous problem. Once the box is moving, mu k is 0.49, so mu k is given as 0.49. How much force will you need to apply? So we're finding the applied force again to keep the box moving at constant velocity. All right, well, we know that at constant velocity, it's at equilibrium. So let's draw our free body diagram again. So our weight was given, and it was 25 newtons. Our normal force points perpendicular to the surface, opposite the weight in this case. We're still going to be moving it to the right. And now, because it's kinetic friction, we'll put a little k for a subscript. How much force will you need to apply to keep the box at constant velocity? Well, let's sum our forces. Again, we're treating this as a problem, as a new problem. So let's imagine we have not summed our forces on the previous slide. Let's do the y first. Sum forces along the y. We know that the weight vector minus the normal force vector would equal 0 because we know this object is at equilibrium and the forces balance out to 0. We know that the weight of the box is 25 newtons. Therefore, we know the normal force is also 25 newtons. What else do we know? Well, if we were trying to sum the forces along the x, we know that the friction kinetic, whatever it is, minus the applied would also equal 0. And again, that's because it's at equilibrium, because constant velocity means equilibrium. Do we know either one of these? No, we don't. So this becomes very similar to our problem from earlier. So on the previous problem, we had to find the friction force because we knew that the friction force kinetic friction force kinetic was equal to the coefficient of kinetic friction times the normal force. And that means that if we knew mu k, hey, we know mu k is right there, 0.49. And we knew the normal force is right there, 25 newtons. That we could figure out what the kinetic friction force is. So the kinetic friction force would be 12.25 newtons. And if that's the case, and the 12.25 newtons of kinetic friction force is going against the applied force, we also could solve for the applied force. The applied force is the same value. So that would be our answer. If you go back and you look at pure than the 12.25, and that goes back to our idea about keeping an object moving is easier than getting it to start moving. And that's a first law concept. Objects like to keep on doing what they're already doing. So if something is already moving, it wants to keep on moving. All right, our next problem says you're pulling a 150 Newton box at a constant velocity with a rope at 50 degrees relative to the ground. You're pulling with 70 newtons of force. Calculate the normal force, the friction force, and the coefficient of friction. So a lot to do on this one. All right, so let's go ahead and draw our crate. Actually, let's do it in black. Draw our crate. Go ahead and put our floor down there. All right, what are we going to put in first? Well, we're going to have a coefficient, a force of weight pulling down. And we actually know that value, it's 150 newtons. And we're going to be pulling up with a normal force. You might think, oh, that's 150 newtons too. Well, not this time. And we'll talk about why that is in a second. You're pulling with a force of 70 newtons. So I'm going to put an angled vector here. And we're going to label that the applied force. And that's 70 newtons. And it gives me a value for an angle of 50 newtons, or 50 degrees, sorry. So this angle is 50 degrees. Is there a friction force in this problem? Well, it's asking us to find the friction force, so yes, there certainly is. Which direction will it point? Well, remember, this box is moving along the ground. It's not being lifted up into the air. So it still has a motion that's parallel to the surface. So that means that the friction force is going to go opposite the motion, parallel to the surface. So I'm going to draw my friction vector opposite, like so. And we're going to label that friction kinetic. All right. Now there is one extra thing we have to do on this one that we didn't have to do on our previous problems. This FA vector is at an angle. It's not following along the x or the y axis. And because of that, we're going to have to draw the components of that 70 newtons. Well, what was the rule about x and y components? They always formed a right triangle. And I want to incorporate the 50 degrees, so I'm going to draw my x component first. It's going to come out, it's going to follow the x-axis. Put a little arrowhead on it, like that. I'm going to label it force applied with an X on the end. So kind of like if you say fax, that's so nonsense word. That's your fax component, your X component. And then I'm going to draw up from there my Y component. And I'm going to label that force applied for my Y. So sometimes we say fax and fay. And where's that 90-degree angle that the two components make? It's right there. All right. So now we have finished our free body diagram, and we're ready to solve for our forces. And to do that, we're going to have to sum our forces. Let's go ahead and write what we're trying to solve for. We're trying to solve for the normal force. We're trying to solve for the friction force. And we're trying to solve for the coefficient of kinetic friction. So we have to find the normal force, the friction force, and the coefficient of friction. I always find that on problems like this, it's easier to go ahead and sum your forces first, and then see what you have and what you don't have. So let's take a look here. We know that if I sum the forces along the x-axis, I see only two vectors that go along the x-axis. I see the friction vector, and I see this red x component. So I'm going to sum those forces. Now, the question said constant velocity. Now, constant velocity means this is an equilibrium. This object is at equilibrium. And that means that the sum of the friction force and the x component should balance out. In other words, they should be the same value, they're just different directions. So if I happen to take the x component, which we're calling Fax, and I subtracted it from the friction vector, I should end up with 0. Well, how would we calculate the x component? It looks like it's an adjacent side to the 50 degrees. And we know the hypotenuse is 70. So if I know the hypotenuse is 70 and I know the angle, I can use cosine of the angle times hypotenuse to find the x component. So that would be 70 cosine 50 degrees minus my unknown, my friction force. I know that equals 0. Well, 70 cosine of 50 is 45 newtons minus the friction force, which means that the friction force is 45 newtons. And that's my first answer. That's one of the answers that they wanted me to find up here, friction force. All right. Well, let's sum the forces along the y-axis. And let's think about, what do we have along the y-axis? We have the normal force vector. We have the weight vector. Is that the only two vectors that go along the y-axis? Well, if you look closely, you also have this y component of the 70 Newton applied force. So we have to incorporate that into our summing of forces. Another thing is, again, this is at constant velocity. So the sum of all the forces pushing up minus the sum of all the forces pulling down should equal 0. That's a rule. If you're at constant velocity, you're at equilibrium. So let's sum the forces along the y. And what do we have pulling down? Looks like we have FW. Is that the only thing that you're pointing down? It is. So I'm going to subtract from that. Well, I'm going to subtract two things. I'm going to subtract the normal force, whatever it is, plus the FAY, the y component of the 70 newtons. So I'm going to put that in parentheses just to remind myself that they point the same way. And why am I adding them in the parentheses? I'm adding them because they both point up. If they both point up, they're both positive. And all of that should equal 0. Well, FW I know. I know FW is 150. It was given. FN, don't know that. FAY, well, isn't FAY opposite the 50 degrees in our triangle? And if I know the hypotenuse is 70, I could use sine of 50 times 70 to find the y component. So I'm going to do that. So 70 sine 50. So 150, I'll just drag that along with me, minus Fn plus, what's 70 sine 50? Well, 70 sine of 50 is 53.6 newtons. And that's going to algebraically end up giving me 96.4. Because what's going to happen is I'm going to end up subtracting 150 minus 53.6. That's 96.4 newtons. Well, there's a second answer. That's what else they wanted me to find. And then the coefficient of friction, well, let's think about that. We know the coefficient of friction, in this case kinetic, times the normal force is equal to the friction force. That's a formula right off of our formula sheet. So I could solve for mu k by dividing both sides by normal. And do I know the friction force? I do, it's right there, 45. Do I know the normal force? Yes, it's right there, 96.4. And I divide that out, and I end up with a mu value of 0.467. Remember, there is no unit for coefficient of friction. All right, your guitar is sitting on a hill at a 10-degree incline. Why is it sitting on a hill at a 10-degree incline? We don't know. It just is. It weighs 100 newtons. What is the value of the friction force acting on the guitar? What is the coefficient of static friction between the guitar and the ground? All right, so for this one, we're going to have to draw an inclined plane. And it really doesn't matter whether you draw it up and to the right or up and to the left. It makes no difference. I'm going to usually draw mine up and to the right. And do I need to draw an actual guitar as my object? Well, you can if you want to, but usually it's just faster, it's more efficient if we draw just a box, just a rectangle or square to represent the object. So I'm just going to draw a little box here. And that represents my guitar. Put a little dot in the middle. And now I'm ready to draw my, don't forget that's a 10-degree incline right there. Ready to draw my vectors, all right? The weight vector, now remember the weight vector goes straight down, It does not go perpendicular to the surface of that incline. So that's FW. Do they give us FW? Yeah, they do. They say that it weighs 100 newtons, so we're good there. Which way is the normal force going to point? Well, the normal force is going to point, remember, perpendicular to the surface. Perpendicular to the surface would be like this. Label that Fn. All right, is there friction? Well, there better be. They're asking us for a friction force. Is there potential for this object to slide down the hill? There is. There's just friction holding it in place. If we took the friction away, it would slide down the hill. So we always draw our friction vectors in the opposite of the motion or intended motion. In this case, the intended motion is down the hill, so we draw our friction vector up the hill. And what type of friction is it? Looks like it's static friction. It's not moving. All right, one more thing we can do. We can draw the components of our weight vector. And remember, the rule about drawing components is they always make a 90-degree angle. So I'm going to draw my two components. I'll draw my y component, starting from the center of the object. And a lot of students want to know, well, where do you stop? Remember, it has to make a 90-degree angle. So you stop about right there. And then my x component would be right here. And again, that 90-degree angle is right there. Okay, let's label our components. This is FW, which one would it be? Well, it's going up and down relative to the incline, so it's FWY. And this is going side to side according to the incline, so it's FWX. And we also know this angle right here is 10 degrees. All right, so our free body diagram is done. So what are we supposed to do? We're supposed to find the friction force. And we're supposed to find the coefficient of static friction. Well, to find the coefficient of static friction, what do I need? Well, I need, if you think about the formula, it's force of friction equals coefficient of static friction times the normal force. So if I'm trying to find the coefficient of static friction, I would divide both sides by normal force, and I end up with that setup. Well, I don't have either one of these. I don't have the friction force, and I don't have the normal force. So let's talk about how we would go about finding the friction force. Again, let's sum our forces. So if we sum the forces along the, what do we want to do first? Let's do the y-axis first. What components or vectors follow the y-axis relative to the incline? In other words, what vectors are perpendicular to the incline? Well, it looks like Fn's there, and it looks like Fwy, even though it's going the opposite way, is there. Now it says this is not moving, so it's at equilibrium. And what that means is that the two components, the vector and the component, pointing opposites from each other, should equal the same value, and if they're going opposite each other, then we should end up with 0 if we're summing them together. So, is there a way to find Fwy? Well, I know Fwy is a side that is adjacent to 10 degrees, and I also know that the hypotenuse, remember, this value here, this 100, is the value for the hypotenuse of this right triangle. So I know the hypotenuse is 100, and I know the degree. I can find Fwy using cosine. So Fn minus the hypotenuse, 100, times the cosine of 10 equals 0. Well, the cosine of 10 times 100 is 98.5, and that means that the normal force is 98.5. Now, is that something that the problem told us to find? No, but we need it down here. So we're going to be using that 98.5 later. What else can we sum? We can sum the forces along the x-axis. So what forces do you see going along the x-axis? Well, I see, remember, that would be parallel to the surface of the incline, right? So I see a friction force, and I see a component of the weight vector, Fwx. So those are the only two along the x-axis, and it's at equilibrium. So I know if I sum them together, I'm going to get 0. So FFR, so the static friction force, minus the vector that goes the other direction, Fwx. If I sum those together, I'm going to get 0 because it's at equilibrium. That's how I know to set it to equals 0 every time. Is there a way to find Fwx? Well, it's opposite the 10 degrees, and I know the hypotenuse is 100, so I can use sine to help me find that component. So 100 sine of 10 degrees equals 0. So if we do the 100 sine of 10, we end up with 17.4, and we know that that is going to equal the friction force as well. So I now know the friction force. And that is one of the things they ask us to find up here, right? Do I have enough information now to find the coefficient of friction? Well, I know normal, and I know friction force, so I'm good. So plug and chug now, 17.4, which is the friction force I solved for, divided by 98.5, which is the normal force that I solved for. And I end up with a coefficient of friction of 0.177. And that is my coefficient of static friction. Your 80 Newton physics book is sliding down a 30-degree incline at constant speed. What is the value of the friction force acting on the book? What is the coefficient of friction between the book and the ground? So this is pretty much asking you the same thing that the previous problem did, except this book is moving, but it's at constant speed. So we know that that means that it's at equilibrium. So we can still use the same concept as the previous one. But let's draw out our incline first. So draw it up and to the right again. It doesn't matter if you draw it up and to the left or up and to the right. Makes no difference. It's 30-degree incline. I'll go ahead and put that in there. And I'll draw my book. Again, it doesn't have to look like a book, but a book's kind of rectangular anyway, so it's going to look like it. Put a little dot in the middle, and now all my vectors are going to go from the dot outward. Which way is that FW going to go? It's going to go straight down. Do they give us the value? They do. It's 80 newtons. And what about that normal force? Normal force is going to be perpendicular to the surface of the incline, so it's going to go straight up like this. That's normal. Which way is the book moving? It's sliding down the hill, so friction force is going to go up the hill. Parallel to the surface, and it's kinetic friction. And the last thing I would do is draw the components of my FW vector. So, which one should I draw first? Well, I'm going to draw the one coming out of the object first. So, in this case, the book. So there's my Y component. Again, it makes a 90-degree angle. That's how I know to stop about there. And then draw my Y component. Label. This is FWY. This is FWX. And now I have finished drawing my free body diagram. Probably should have made my FWY a little longer so that the blue line, I want the blue line for the FWX, I want it to be parallel to the inclined plane. So it should be a little bit longer, but it looks fine. All right, so what do we need to find? We need to find the friction force, and we need a coefficient of friction. Well, if you remember on the last one of the things we did was we wrote out the formula for the coefficient of friction. And we know that it's mu k times normal gives you the friction force. And since we're solving for mu k, we know that's going to be the friction force divided by the normal force. And we have neither one of these. We don't have either one. We don't have friction force. We don't have the normal force. So again, let's set out to sum our forces. We'll start with the x. Doesn't really matter which one you start with. Let's sum the forces along the x-axis. And what do we have? We have the friction force is going along the x-axis, and the x component of the weight vector is going along the x-axis. So I'm going to sum those. So it's going to be friction force minus FWX. FWX is the x component of the weight vector. The reason I know that these would equal 0 if I subtracted them is because it's at constant speed. So I know that it is not changing direction, and I know it's not speeding up. I know it's not slowing down. I know it's at equilibrium. So we set those equal to 0. Is there a way to solve for FWX? Well, let's see. I did forget to put in one of these values. I do know that the angle here is 30 degrees. So if I know the angle, and I know FWX, which is opposite the 30, and I also know that this is 80, the hypotenuse is 80, I could multiply the hypotenuse times the sine of 30 to get that side. And since I know they cancel out to 0, I know that that value, whatever it is, 80 sine 30, I know that value is the same value for my friction force. And that just happens to be 40 newtons. And that is one of the things they wanted us to find, the friction force. And I know I'm going to need it down here later on. Well, let's sum the forces along the y-axis. Sum the forces along the y-axis. What do I have along the y-axis? What's perpendicular to the surface of the incline? Well, it looks like the normal force is perpendicular to it, and the y component of the weight vector is perpendicular to it. So, should they add up to 0 if I sum them, if I add them together? They should. So let's do that. Fn minus Fwy equals 0. Fn I don't know, but is there a way to solve for Fwy? Well, Fwy is adjacent to the 30 degrees, and I know the angle, I know the hypotenuse is 80. So if I do 80 cosine 30, 80 cosine 30, I should end up with the normal force. And I see that 80 cosine 30 is 69.3. And again, that's not something that we were asked to do, but we need it down here to solve for our coefficient of friction. So we know the friction force, we know the normal force, and we are asked to find the coefficient of kinetic friction, and that is going to be 40 newtons, the friction force that we solve for, over the normal force that we solve for, 69.3. And that gives us a value of 0.577. And that is our coefficient of kinetic friction. All right, you're pushing your friend up a steep 11-degree ski slope. Your friend weighs 650 newtons, and you must push with a 347.5 newtons to move at a constant velocity. What is the coefficient of friction between your friend's skis and the snow? All right, again, first thing we should do, draw our free body diagram. So let's go ahead and do that. I'm gonna have, again, it doesn't matter whether you draw it up and to the right or up and to the left. Makes no difference. And again, we don't have to draw an actual person. We can just draw a rectangle to represent the person. And let's start drawing our vectors. We know that down is going to be the weight vector, as always, Fw. Are we given the weight of the skier? We are, 650 newtons. Where is that normal force going to go? Well, the normal force is going to go perpendicular to the surface. So we're going to draw a vector going like that. And we'll label that Fn for normal force. All right, now we are pushing our friend up the hill. So we are applying a force to our friend. So our hands, our arms, our muscles are pushing. So we are applying a force to this object. which way is that force being applied? Up the hill. So we're going to draw a vector up the hill, and we're going to label it FA, applied force. And they give us the value for that applied force. They say it's 347.5 newtons. All right, let's draw our components for our weight vector. We always start from the center of the object, and we draw our FWY. Again, we know that they are going to make a 90-degree angle. And then we draw our FWX. And we label FWY, FWX. And we remember they always make a 90-degree angle. There's that 90-degree angle. You might be thinking, oh, well, we're done. Well, this one's a little different. If you go back and look at the other couple of problems we've done previously, we always pointed friction up the hill. We pointed it up the hill. But that was because the intended motion, or the actual motion, was down the hill. Well, which way is the motion this time? The motion this time is up the hill. So which way should friction point? Well, remember, it's always opposite the direction of the object's motion. So we're going to point friction down the hill. And what type of friction is it? It is kinetic. Kinetic friction. All right, so I think we are done with our free body diagram. All right, so what are they're asking us to find the coefficient of friction, right? They're asking us to find the coefficient of friction, and that means that we need two things. We need, remember that the friction force, in this case it's going to be kinetic, is equal to the coefficient of friction times the normal force. And that means we know that the coefficient of friction is equal to the friction force divided by the normal force. Well, we don't know either one of these, unfortunately. So that means that we have to solve for friction force, and we have to solve for normal force. Of course, we know that we're going to have to sum forces as well. So let's go ahead and sum the forces. We'll do the forces along the y first. Sum the forces along the y-axis. And what forces do I have along the y? Looks like I have two of them. Remember, these will be the ones that are perpendicular to the incline. I have normal force, and it looks like I have the component of the weight vector. So if I sum them, F normal minus FWY should equal 0. Well, there's no way I can find normal force without solving for FWY. And let's think about, well, we need to go back. I forgot to put something in my free body diagram. We forgot this 11-degree slope. So 11 degrees right there, which means it's 11 right there. Okay. And if we know the angle is 11, and we know that the hypotenuse, remember this would be the hypotenuse right there, 650, we know we can find FWY, the adjacent side to the 11 degrees. So it's going to be the hypotenuse times the cosine of 11 degrees. And because it's at equilibrium, and I know it's at equilibrium because of constant velocity, we know that it equals 0. So what is 650 cosine 11? Well, that's 638.1 newtons, which means I found the normal force. which is something I'm going to need later to help me find mu k, the coefficient of kinetic friction. All right, let's sum the forces along the x. This one's a little different than the previous ones because in the previous ones we only had 2 forces that were going along the x-axis. But here we're going to actually have 3. So take a look at the picture here. What do we see pointing down the hill? Well, I see the friction forces pointing down the hill, and I see FWX is pointing down the hill. What do I see pointing up the hill? I only see one. I see the applied force. So when I sum these forces, I got to make sure that the friction force and the FWX, the x component of the weight vector, got to make sure that I add them together because they're pointing the same way. And then we're going to subtract from that the applied force, which is 347.5. All right, so the applied force minus the sum of the friction force plus the x component of the weight. Now again, the reason I'm adding those together is they are pointing down the hill. They're both pointing the same direction. And all that should equal 0. So are there some numbers that we know? Yeah, we know applied force is 347.5. Do we know friction force? No, we don't know friction force, but we're about to find it. Plus FWX. Is there enough information for you to find FWX? Well, FWX is opposite the 11 degrees, and I know the hypotenuse is 650. So I'm going to use the sine of 11 times the hypotenuse, 650, sine 11, to help me find the friction force. Because I'll know this is still 347.5 minus my unknown, in this case the kinetic friction, plus whatever 650 sine 11 is, and that's 124.0 newtons. And if we do a little algebra here, we know that we're in the end going to be subtracting 124 from 347.5. So the friction force is equal to 223.5 newtons. So that's my friction force. And do I have enough information now to find the coefficient of friction? Well, it's right here. It's right here. The coefficient of friction is equal to the friction force divided by the normal force. What's the friction force? 223.5. What's the normal force? 638.1. So when I divide those out, I get 0.350 for my coefficient of kinetic friction.